quite a bit today. So one of the things I'm going to do, you see something over here on the shared screen that you probably haven't seen before. This is done in a program called Maple. I'm going to use this because there's a couple things in there that I want to show you that I can't do in CalcPlot3D. But I'm not going to ask you to do anything in CalcPlot3D that can't be done in CalcPlot3D. So don't worry about that. Also, I'm also going to have the PowerPoint up on the other screen. So if you can't read it that well for you folks at home, you could always bring up the PowerPoint from more. All right, so I'm going to go through some stuff, and then I'm going to give you guys the worksheet, which is going to have you try and create some shapes with CalcPlot3D. So I need to set you up for that. All right, let's talk about something we did first half of the semester, which was parametric curves in 3-space. This was our space curve command. All right. That's when x, y, and z were parametric equations of a function, let's call it t. And we did things like a helix, a conical helix, so on and so forth. So space curve is also in Maple. We get basically the same thing. Okay, so you can see when I'm using the space curve command, here I'm entering it as a vector valued function. And then there's the range on x. Because I'm going to give you some a PDF that has examples from Maple, but those same commands can be used in CalcPlot3D. It's just I can print it out, or I can create a PDF easier from Maple than I can from CalcPlot3D. Now, one of the things that I can do in Maple that I can't do in CalcPlot3D, and that's okay, I just want to show it to you guys, is I can do space curves in other coordinate systems. For example, I can do a space curve in spherical coordinates. Okay, so spherical coordinates goes rho, theta, phi. So 10 is going to be the radius of the sphere. 8t is going to give us how many windings, and then t takes us, that's that phi that goes from the positive z-axis down to the negative z-axis. So because we're using spherical coordinates, it's very easy to make a spherical helix. Again, this is some stuff I wanted to just show you that we can do space curves and parameterized surfaces in cylindrical and spherical coordinates. CalcPlot3D doesn't have that ability, and I'm not going to ask you to do anything like that, in here today or on take-home problems. But I just want you to see what it looks like and that it's possible. We've been introduced to those coordinate systems. We should take a look at what it looks like. So, we could parameterize a curve in spherical coordinates. Again, it goes rho, theta. So theta is the windings. And then phi is what takes it from the positive z-axis to the lower z-axis. So it allows us to do some stuff that we couldn't do in CalcPlot3D. But again, it's not going to be stuff I'm going to ask you to do. I just want you to see it. Okay. Let's talk about parameterized surfaces. I'm going to build up to this a little bit. So first off, if these were our sets of equations, this is something we have seen before. If x is cosine t, y is sine of t, and z is just 0, that actually just puts us in the xy plane. And we're basically looking at cosine and sine, which just gives us the unit circle. Except we're looking at it in 3D. All right, so that's what that set of parametric equations gives us. All right, well, let's start to mess around with z a little bit. We know the cosine and sine give us a circle. What can we do with that circle? Well, what happens if I make z be 3? Well, moves it up, right? Because now our circle's in the plane z equals 3. This is, again, nothing new. This is space curves. This is stuff we did way back in module 2, I think. All right, now let's start. And now if we let it equal t, well, this is just our helix. We've seen this before. So where parameterized surfaces come in, we need another variable of parametrization. So if I let cosine and sine be t, but now I let z be something else. You know, like in CalcPlot3D, we'll be using u and v. We might use theta and r. We could use t and s. By introducing that second parameter, we now are going to get a surface. So let's think about what's going on with this surface. Cosine and sine, we know, make a circle. That's basically the unit circle around the z-axis. So by letting z vary now too, that creates our cylinder. Okay, that's basically, there's our circle from cosine and sine. And then by letting z be a second parameter, that makes it go up and down. Now, it's not a coincidence that we're getting a cylinder of radius 1. Our equations should be related. So if you remember, the formula for a cylinder of radius 1 was x squared plus y squared equals 1. Well, if x equals cosine t, right, and y equals sine t, we'd have cosine squared plus sine squared, which also is equal to 1. All right, because one of the things I'll ask you to do in the worksheet is you're going to parameterize a paraboloid. Well, if you plug in your parameterization into the equation of a paraboloid, everything should still be equal. And that's one of your ways of being able to check. All right. Now, like I said, I'm going to do some stuff in Maple that, you know, that we won't be able to do in CalcPlot3D, and that's okay. So I just want to differentiate one more time. In the first couple of cases, we had a parameterized curve in 3-space because we only had one variable of parameterization. Now we have parameterized surfaces because we have 2 of them. All right, so x, y, and z can be functions of up to 2 variables, and those 2 variables are going to have a range. Okay. We can do these in cylindrical and spherical coordinates also. Like I said, CalcPlot3D doesn't have that ability, but you know, obviously we need to be able to do a cylinder in cylindrical coordinates. So we would just set the radius to be 1, let theta go from 0 to 2 pi to make the circle, and then again let z be some other parameter. And there's the same cylinder, this time in cylindrical. A cylindrical coordinate parameterization. That's not going to be something we're going to do because CalcPlot3 doesn't have the ability. But again, we've seen cylindrical coordinates, so I want you to be familiar with it. Now, next thing is a sphere. So a sphere, obviously, is going to be easier to do in spherical coordinates. But again, we're not going to be able to do that. But those conversions that we got, you know, that we used on the note card back for the midterm, those are the parametric equations for a sphere. Those exact ones. So sine phi cosine theta, sine phi sine theta, and then cosine phi. That gives us our sphere of radius 1 centered at 0, 0. If we put a number in front of all 3 of those, that'll change the radius of the sphere. That's going to be one of the things you're going to get to play with today. Again, it's a sphere. Of course, it's going to be easier to do in spherical coordinates. That would just be rho is 1, theta we'll just let to go from 0 to 2 pi, and phi will let go from 0 to pi. And we get pretty much the same thing. So nothing too interesting yet. So we're going to get into some more interesting stuff, like a torus, which kind of looks like a donut or a bagel, depending on your preference. All right, so there's a couple different ways of thinking about a torus. There's two different circles we can look at because it's basically the combination of two circles, right? One circle going this way, which would be parallel to the XY plane, and then one here, which is perpendicular to the XY plane. So we're going to look at a torus, and we'll look at, I do want to show you that these can be done in CalcPlot3D, so I'm going to switch back and forth. But here's what a torus would look like in rectangular coordinates. Again, one of the things I'm going to have you guys are going to play around with these equations to get it to have different sizes. Like I said, this can be very easily done in CalcPlot3D. And there's our torus. If we want to give it a little bit rounder shape, we can increase the number of steps, right? But there's the torus. It can be done just as easily in CalcPlot3D for rectangular. Like I said, there's a couple reasons I wanted to use Maple just because I want to show you some stuff. So if I cut this torus in half, one way of thinking about the torus is this circle here, centered out at 2, is being rotated around the z-axis. Call that a generating curve. All right. There's going to be 2 different generating curves for this torus. Let me show you what I mean by that. This is going to be it was just easier to do in cylindrical, but I want you to see what I'm talking about when I say a generating curve, right? So this curve is called a generating curve. Now, when we do multiple of them, they're called parameter curves, and we'll talk about that a little bit later. But if you imagine this curve being rotated around the z-axis, it creates the torus. What's that? It generates, yep. And the reason that this is important is because this starts to help you get the relationship between the equations and what you're getting. So to get this curve, what I did is I kept one of my parameters, in this case, u as a variable, and I turned v into a constant. Notice there's no v in there. So what that does is it's like looking at traces of 3D plots. We're only looking at a 2D object at a time. So we're only looking at a space curve to see what it looks like. What is u creating and what is v creating? So what's happening here, this thing gets rotated around like such, creating the torus. Now we could do it the other way. So now I'm holding u to be constant because I don't have a range on u. And so now we're getting this circle, here. I'm sorry, we're in cylindrical. We're getting this circle of radius 3, which is coming from the 2 cosine of theta. This could generate the torus as well this way, right? I mean, can you kind of see it? Yeah, it's I think this will be a little easier for you to see, right? Oh, I'm a little slow. Come on. There we go. That's a generating curve because what we're doing is we're taking the curve in 2 space, a 2D curve, and then we're adding that second parameter to make it a surface. And again, the reason I really emphasize this is what's given me that curve is setting one of the variables to be a constant. And we'll look at that again when we look at parameter curves. The reason that that's important is because that really helps us see how these things are being created so that we know, okay, if I want to change the radius in this direction, well, I need to change the parts that depend on u. Or if I want to change the size in this direction, I need to change the parts that depend on v. Okay, and you can tell by setting one of them to a constant to see what it looks like in terms of the other one. We can do the same generating curve trick here. Again, this is why I'm using Maple. I just want you to see what's happening, right? Kind of looks like a slinky. But you can see how that circle, right? That circle comes from setting, in this case, V to a constant. But then we let V vary, and we get the 3D surface. All right. So this is going to be something you're going to get to play around with, because until you get to play with them, you don't really get a full understanding of them. And I'm going to give, like I said, I'll give you a PDF with some examples. But I want to show you some of the other stuff we can do. This is kind of cool. A generalized torus. So we looked at a circular torus. What if we wanted some torus that was a triangle and we wanted to rotate that around the z-axis? It works the same basic way. Remember what we just saw? I took the circle and rotated it around. So what I need now is the parameterization for that triangle, but then the same equations that rotated the circle around will rotate the triangle around. Now, because it's a triangle, it has to be done piecewise. Again, this is not something I'm expecting you guys to do. I just wanted you to see how this stuff generalizes. We're back. Sweet. All right. So I'll show you the triangular torus since we talked about that. That's what that thing would look like, that triangle being rotated around. We can animate that. So that's that triangle in the XY plane. Rotate that thing around. One of the things that's kind of interesting about CalcPlot3D. So when you go to do a parameterized surface, parametric surface, the default one is the sphere. Cool. So if you need to make a sphere, it's the default one. I'll show you something else real cool here in a little bit, but I don't want to show you just yet. Okay. So we can do that. We can rotate a torus. We can parameterize planes. I'll give you an example of a plane here, but if you have a plane that goes through a point and two non-parallel vectors, this would be the equation. This here is the equation of that plane. All right, so this would be your three parametric equations that would make up a plane. And again, all you need there is two non-parallel vectors and a point that it goes through. Parameterizing surfaces of revolution. This is what we were just doing with that generalized torus, or really anything. We can do this with a cone. We can do this with we can think of anything that is symmetric about the z-axis. We can think of it being rotated around the z-axis, right? And so one way of doing a cone is to create an equation for the line in, say, the ZY plane, and then rotate that line around the z-axis. And how do you do that? Well, you're going to have a function of z representing the line. So what I mean by that, here's your, we could do it xz or yz. So you would do your line here, and in this case, we do it as a function of z, and we could rotate that thing around whichever axis we want. All right. We could go around a different axis. Now this is going to go around the z-axis because it's f of z cosine theta, f of z sine theta. But we could do f of y cosine theta on the first part, and f of y sine theta for the z coordinate if we wanted to go around the y-axis. So this will work for any axis. We got this back. So if we wanted a cone that has a base of radius 3 in the xy plane and a height of 10, what we do is we create an equation for that line. This is our f of z. 3/10 times 10 minus z is going to give that thing, is going to give us that linear function. Because we have a slope of 3/10 in the xz plane. So there's our cone. We can rotate basically any function around there. And again, we can change the axis of rotation. Let's do one in CalcPlot3D. So, I mean, we can think of this as being rotated around the z-axis too, right? We're rotating a circle, this half circle, around the z-axis. But let's see, we could do, so if we're going up, so we could have e to the v. So this would be our exponential function, e to the v, and then we'll just let z be v. U is going to go from 0 to 2 pi, v, let's just have go from 0 to 3 right now. All right, it's exponential, so it grows pretty fast. A little smaller. And so you can see how we get our exponential function here. Now remember, I'm doing e to the v, which is why it's opening out this way. But you can see our exponential shape there being rotated around the z-axis. So if you put some negative on there, it'll actually look a little better. So that's what this slide was saying, is you can take any function and rotate it around the z-axis. Parameter curves. This is something, if Maple comes back up, I'll show you what it looks like for a cylinder. So remember I talked about the generating curve, right? That's looking at setting one of your variables to a constant, looking at what you have in as a 2D plot in 3D to get an idea of which variable does what. Parameter curves are a set of those, all right? So, in Maple, I've got it done for a cylinder, but I have it in CalcPlot3D done for our torus. So there's our torus. A set of parameter curves would look like this. Does that make sense? So what I did over here is I put in the exact same parametric equations, except I was set one of the variables, and it has to be done as a space curve in CalcPlot3D. So instead of having the two variables, u and v, I just have the one variable. The second one I just set to a constant, and I just started at 0, 1, 2, 3, 4, 5 to make the 6 parameter curves. And you can kind of see how they make up the torus. All right, so if you ever ask for parameter curves, what you're doing is basically plotting space curves while setting the other one of the variables, one of your parameters to a constant. And each different constant produces a different parameter curve. But you should see the makeup of your 3D surface, right? We have enough here to see, oh, okay, we have some kind of donut shaped thing going around the z-axis. So those are what parameter curves are. That is something we can do in CalcPlot3D. Just realize if you're ever asked to do parameter curves, you have to do them with the space curve command, because you're just doing the one-dimensional lines, not the surfaces. Okay, so parameter curves for a cylinder there. So you can see by setting the vertical component to constants, we get the concentric circles, which we can see make up the cylinder. That's one set of parameter curves. The other set, so you can see them together. Right, so there's that generating curve. Now, there's another set of parameter curves because now I can hold the input on X and Y as a constant and just let the other one vary. And so there's the other set of parameter curves. Every surface will have two sets of parameter curves. One when you hold one variable at constants, one when you hold the other variable at constants. Okay. Surface area, we've talked about this before. You guys have actually done this before because we did it back when we did surface area last module. We started with the surface area of a function. We talked about surface area of a parameterized surface, even though we hadn't seen it yet. So if you remember where this comes from, we talked about it that day. Remember that the magnitude of the cross product gives the area of a parallelogram. So what's happening is, we've got our UV space and it's broken up into a bunch of rectangles, but R, doesn't look like an R, but R takes this and maps it onto our surface. And so if you remember, we break that surface up into a bunch of parallelograms, and each area of a parallelogram comes from the magnitude of the cross product. The double integral sums them all up. Now, here's what's really nice about doing this. And we talked about this last time. Once you have a parameterization, okay, so like if we're doing surface area of a sphere, let's say, once you have the parameterization for the sphere, you can finish this off because everything is procedural after that. First off, you do your partials with respect to each variable. The order of the cross product does not matter because you're taking the magnitude. And then your limits are the same limits from your parameterization, right? So if you're, if we did that cone that we were looking at earlier, if, let's see, where are our limits on that cone, just to remind myself. So if we go back to that cone, if we wanted to do its surface area, right here, well, we have the equation, so we can do the partials, and here's the limits, 0 to 2 pi and 0 to 10, all right? There's no trying to figure out what the region is in the XY plane like we had to do last time with our double integrals. That's the nice thing about surface area of a parameterized curve. Once you have your parameterization, all you got to do is take your partials, do the cross product to get your integrand, and the limits that create the surface are the limits for your double integral. So as long as your plot looks like exactly what you want, you now have the correct parameterization and your correct limits. So you'll get to do one of those as well. Okay, a couple of things I want to show you. All right, first off, and this is, everybody has access to this. If you're not logged into more, you can go ahead and log in. So I put it on the calendar so you can find it very easily. Here's those parametric surfaces we were just looking at as a PDF. All right, so you'll have access to the equations there. There's your torus. It's everything that we just looked at, the plane, the cone. So you're going to be able to use those as you guys practice. And there's your parametric curves. Here's a couple other crazy things, a vaulted torus. I think you might ask him, I think you're going to get asked to make one of those. Helicoid. The Mobius strip. All right. Okay. This is pretty cool. Now I'm going to show you something else that I think is pretty cool. Two things that I think are cool. Number one, CalcPlot3D. You do not need to memorize all these equations. I gave you that PDF. I don't expect you to memorize these equations. But check this out. If you go to examples, look at what they have under examples, parametric surfaces. Look at what they have right here, the Mobius strip. And if you wanted to know why you want to care about the Mobius strip, it only has one side. So why is that interesting? Teacher said we were allowed a note sheet, but we we're only allowed to use one side. Turns out if you make it out of a Mobius strip, you get to use both sides of the piece of paper. So for us, if you do note cards, you get both sides, so you don't have to turn them into a Mobius strip. But if you're ever in that situation, there's a useful, and you guys wondered when you were ever going to use this. Yeah, basically. But I encourage you guys, the rest of the time we're going to do playtime. There's a whole bunch in here. Look at, here's the Taurus, a tilted, there's our Taurus, an ellipsoid, which we've seen as in rectangular, but here it is in as a parameterized surface. Hyperboloids we've seen before. If you want to just kind of see what some of this stuff looks like. Helix tube, that's kind of like our vaulted, that's basically our vaulted torus. So, okay, so the rest of the time we're going to spend on the computers. And what I thought might be interesting is to give you guys an opportunity